This is part 2 of a series of videos on the Foenix F256 and the 6809. In this video, I'll go into some fundamental OS9 concepts. OS9 Level 1 started out in life as an embedded operating system. It was designed as a small kernel meant to live in a ROM, although its modular nature allows it to be extended to connect to disk devices, as we'll see in a bit. It's this modular feature that allows OS9 to fit nicely within the flash of the F256. Level 1 can address a maximum of 64K, so its utilization of memory is limited. OS9 Level 2 is a more powerful version of OS9 that takes advantage of systems with larger memory sizes like the F256, but I'll talk about Level 2 in another video. People new to OS9 often try to rationalize the operating system by comparing it to something they know. OS9 was inspired by Unix and has some Unix-like features, so comparing it to Unix or Linux is apropos, but I want to emphasize that OS9 is not a variant of Unix. It's its own operating system with its own set of commands, features, conventions, and principles. Let's do a quick review of the memory organization in the F256 when it powers up with the 6809 installed. In the previous video, I showed this slide. It illustrates the 512K of flash that the F256 breaks up into 64 8K blocks from 40 to 7F hex. FU is the boot environment that is based on OS9 Level 1. The code for that environment resides in the last 3 blocks from 7D to 7F, and the 40K flash disk image resides in blocks 7.8 to 7C. This occupies 64K of the total 512K of flash available on the F256. When the F256 powers up, the trampoline code and address FC00 configures the dynamic address translation registers such that RAM appears in the lower 5.8K blocks of the 64K address space. This gives OS9 40K of RAM from 0000 to 9FFF to utilize, while the upper 24K still houses the kernel and other parts of the operating system. With the understanding that OS9 Level 1 addresses 64K of memory and fits into the flash of the F256, I'll now go over some fundamentals of OS9, starting with the concept of the module. The module is a central tenet of OS9. It's a package of bytes that contain code or data. Modules encapsulate things like programs, system components like file managers, device drivers, device descriptors, and I'll talk about that shortly. And even the OS9 kernel itself is wrapped in a module. Every module begins with 2 sync bytes, 87CD. Following the sync bytes are 2 bytes that indicate the size of the module. Next is the offset to the name of the module. This is an offset relative to the start of the module where its name string resides. Every module has a name that you identify and address it by. After the name offset is the type language byte. The upper nibble of this byte indicates what type of module it is, for example, a program or a device driver or a data module or a file manager. The lower nibble is the language, and there are representative values for languages such as 6809 object code, Pascal P code, basic '09 intermediate code, and so on. The next byte in the module contains the attribute and revision. The upper nibble of this byte indicates the attribute of the module, such as whether or not the module contains reentrant code. And the lower nibble is the revision, which is useful for tracking incremental changes to the module. Following that byte is the header parity, a single byte that the kernel uses to validate the previous 8 bytes. The kernel verifies a module when loading it into memory by looking at this byte. Following the header parity are different bytes depending upon the module's types, and we'll look at that in a couple of examples later. So once we get past the module header, we are at the body, and this contains executable code or data. It's the payload of the module, and it can be an arbitrary size. At the very end of the module is a 3-byte CRC. That's generated over the head and the body when the module is created. The kernel computes the CRC and compares it to this value when loading the module into memory as an additional integrity step. I have full loaded up on my F256K, and I'll hit S to get into the shell, and I will investigate some details about the module structure in OS9. The first command you should know is mdir. mdir will show you the module directory contents. These are the modules in memory right now on this OS9 system. And I'm going to talk more about these modules later, but for now I just want to focus on the module for the sake of looking at its contents. And I'm going to pick on the echo command. You see echo is on the screen there. It is 1, 2, 3, 4, 5, 6, 7 rows down, second column. And all echo does is it takes a parameter and it just echoes. It's like a print command, very similar to Unix. I'm going to use the ident command, and ident tells us information about a module. And I'm going to use the -m option, which tells the ident command to look in the module directory for the module, and I'm going to type echo. And as you see here, this gives us all the information about the module. The size of it, its CRC, the header parity, where the module's execution address is. Inside the module, there's an offset to the first instruction so that whenever you type the command and it is forked, that's where the instruction starts. There's a data size which tells the operating system how much stack and RAM to allocate for this module whenever it is a process. There's an addition number that is used to identify how recent or how new this particular program is. And then there's the type language that we discussed and the attribute revision bytes in hex. And then the last line summarizes that this is a program module, it's a 6009 object code module, and it's reentrant. I'm going to type the dump command, which is a command that shows the hexadecimal contents of a file or module. I'll use the -m to indicate we want to look at a module in the module directory, and I'm going to dump echo. What you see is the raw contents of this module. It has 87CD as its starting bytes. That's the OS9 sync bytes for a module that says this is where the module starts. Following that are 2 bytes 0022, which is the module size in hex, and that corresponds to the module size you see above in the ident output. Following that are the 2 bytes 000D. That is the offset from the beginning of the module to where the name of the module starts. And if you look in D bytes into the module, underneath the D on the first line is the hex value 45, followed by 63, followed by 68, followed by EF as the first hex byte on the next line. And if you look to the very right, you'll see an ASCII characterization of the dump, and at the D offset is uppercase E, followed by C, followed by H, followed by O as the first character on the second line. And O is actually EF, which is the ASCII character O with the high bit set. So this is how the operating system knows the last character of the module name. It has the high bit set. If you go back up to offset 6, that is value 11, that is the type language byte, followed by 81, which is the attribute revision byte at offset 7. Offset 8 is the header parity of A hex. And then offset 9 is 0012. That is the 16-bit offset into the module where the execution address starts. And this is specific to a program module, because remember, program modules contain executable code, and this particular offset is specific to program modules only. Following that at offset B and C is the value 01C2, which corresponds to the data size, and again is used by the system call that forks a process to determine how much memory to allocate when this module becomes a process. So if you look at the last 3 bytes, F5, FF9A, that corresponds to the module CRC that you see also at the top. Since we're talking about modules, I want to dump another type of a module, and I'm going to dump or actually I'll indent first, a device descriptor. So we have a device descriptor called S0 for the SD card. And you'll see that the output is similar to the program module, but a little different. We don't have an execution offset because there is nothing to execute in a device descriptor. It's simply data. And there's not a data size for the same reason. And the last line shows, instead of saying prog mod or program module, it's device descriptor module. So the type, if you look at the type byte, the type language byte is F1. That F indicates that this is a device descriptor. And if I dump that device descriptor, you can see that it has a good bit of information in it, and you can correspond the output to the ident output above, similar to what I just did for the echo module. Now when I typed mdir, you saw a lot of modules, and I want to go over those modules and their purpose. The most important module of all is the kernel, and traditionally it has been split into two separate modules, kern and kern P2. A kern does the very early initialization of the system and installs a subset of system calls, then calls kern P2, which installs the remaining system calls, performs the video storage initialization, and then forks the first process. The init module is a data module that contains configuration information for the system, and it has no code and is referenced by the kernel at boot time. There are two modules related to system time. Clock initializes the ticker hardware on the F256, which provides a heartbeat for multitasking, and clock 2 interfaces to the real-time clock on the F256 to get and set real time. Let's look at the modules related to the OS9 I/O system, which is based on the Unix concept of a path. IOMan is the module responsible for providing a common I/O interface to applications that want to read and write data. It establishes entry points such as open, close, read, write, and other operations. It also defines the base data structures and concepts, such as the path, that allow data to flow up and down the I/O stack. Below IOMan are file managers in green. SCF is the sequential character file manager and is responsible for character-based input and output. Consecutive devices like video terminals and serial ports are under the SCF file manager. RBF is the random block file manager and defines data structures in the file system for block-based devices such as SD cards, RAM, and flash disks. And Pipeman is the pipe file manager responsible for managing pipes between processes. The blue layer below the file manager layer is the device driver layer. And device drivers are written to exist under a specific file manager, and they interface to hardware from a particular vendor. This is the level in the I/O system that is manufacturer dependent, and you'll see a very different set of device drivers on one computer versus another because they contain different hardware devices. VTIO is the video terminal driver. It manages text on the F256. SE16550 talks to the onboard serial port. For RBF, RBDW is a drive wire block driver and interfaces to a drive wire server. RB Super is a block driver that interfaces to things like SD cards and hard disks. And RBMIM interfaces to flash cartridges and cartridge-based disk images. Piper is just a driver that facilitates communication between processes through pipes. The purple layer below the drivers is the device descriptor layer. And the device descriptor is a module that contains data, no code. It binds a file manager and a device driver together with a number of settings for a particular instance of a device. Here, term is the terminal device for the text screen. T0 is the serial device for the built-in serial port. X0 is the drive wire disk device. S0 is the SD card device. F0 and C0 are devices for the flash and cartridge drives respectively, and pipe is the device descriptor for pipes. OS9 devices are addressable by name, just like Unix. However, that's where the similarity ends. Unlike Unix, OS9 does not use /dev to preface a device. Instead, you preface the device with a slash followed by the device name directly. Here are some examples of OS9 devices and their analog names under Unix. There are a few additional modules that exist outside of the requirements of the OS9 I/O system. These are often called co-modules, and they extend the driver for flexibility. VTIO uses a subroutine module called key drive to facilitate communication with keyboards. For the F256, this subroutine module contains code that interfaces with the computer's built-in keyboard, whereas for the F256 Junior, this subroutine module interfaces with PS2 keyboards. The module is named the same for both computers, but contains different code to address two very different keyboards. The font and palette modules are data modules. They contain no code, and VTIO references them at initialization time to set the video terminal's font and colors. RB Super is the block driver that's architected to work around the 256 byte per sector limitation of RBF by performing sector deblocking of storage devices that have 512 byte or larger sector sizes. It uses a module called LLFNXSD to interface to the F256's SD card. RB Super is an example of a high-level driver that encapsulates a certain amount of generic functionality while delegating device-specific functionality to a low-level module. And again, modules like key drive, font palette, and LLFNXSD aren't defined actors in the OS9 I/O system. They are only known by the drivers that call them, and their call interfaces are defined by those drivers. Let's delve a little bit into the I/O system. I'm going to do an mdir, and you'll see on the first line is the I/O man and SCF file manager, followed by the driver's VTIO, key drive term. Those are modules related to SCF, as was mentioned in the previous slide. Then we have the font and palette modules. Those are actually data modules, and I'm going to ident both of those. Actually, font and palette separately. As you can see, they're identified as data modules, and they're, in the case of the font data, it's somewhat large. The palette data is not that big, but basically just data that the VTIO driver uses to initialize the font and the palette. And since the palette is small, I'll just go ahead and dump it. Everything should fit on one screen. And there you go. You can see the module name at offset D and just some palette data. Let's look at the SD card. Again, typing mdir. The SD card is a block device. RBF is the file manager. That is on the third line, first column, is that file manager, followed by various drivers. There's RB Super and the low-level FNXSD driver there that you see on line number 4. And I will dump the SO descriptor. And when I dump it, you'll notice inside the dump, if you look to the right, you see the text RBF followed by RB Super followed by LL and LLFNXSD. Again, the device descriptor ties the file manager and the device driver together, so it binds them for a specific device. In this case, S0. I'm going to change into the S0 directory and type dir. And you can see that these are the files in the root folder of the SD card. Another important concept in OS9 is the path. A path is a number between 0 and 15 and represents a channel to a readable or writable entity, such as a file, or a terminal, or a printer. Anything that can receive and send data to your program can be accessed through this path. Paths are convenient abstractions for isolating an underlying file or device. It's the central component and concept behind the unified I/O feature that IOMan brings to OS9. Every process inherits 3 paths when it's created. Path 0 for standard input, path 1 for standard output, and path 2 for standard error. And this is exactly how Unix does it. Programs use standard OS9 system calls to obtain a path to a file or device, and then use system calls to read data from that path, write data to it, and then close the path when the program is done. And there are also special status calls that you can make on paths similar to IOCTL calls under Unix. One area that you can use paths is at the shell itself. The shell is the command line interface to OS9 and has similar features to Unix shells. Just like in Unix, the less than operator represents redirection of the standard input, and the greater than operator represents redirection of the standard output. OS9 deviates from Unix in the standard error representation using two consecutive greater thans. Let's take a quick look at redirection using the shell. Let's look a little bit at the redirection and how it works. So I am in the S0 root device. I typed pwd, it tells me that's where I'm at. Pwd is like PD under Unix. It shows your working directory. And I'm going to type the command mdir, but I'm going to redirect the output using the greater than symbol to a file called out. And you'll notice that no output showed, but if I type dir, there is now a file called out. And if I list that file, list is similar to cat in Unix, you see that it contains the text from the mdir command that I ran earlier. I'm going to create a file using the build command, and the build command is simply an easy way to create a text file. When you, well, actually I have to chx into the commands directory. I'll explain that command later, but I will build a file called test, and then it gives me a prompt, and I can just type a command like echo hello, echo world, echo OS9. 3 commands. And then I type enter by itself to get back to the OS9 prompt. If I type dir and I see there's a file called test and I list it, it shows the commands that I typed. Now I can run this as a shell script. The shell will happily execute this as a shell script if I just type test. But what I want to demonstrate is that I can create a new shell and I can take the input from the file and run it the same way. And you can see that it runs it, prints out the prompt each time. I can actually do a -p on the shell to suppress the prompt, and it will echo those commands separately as well as it did the first time, except you don't see the prompt. So that demonstrates the standard input and the standard output of the OS9 shell and the processes. The prox command, which is similar to the ps command, is also another command that shows you for the processes running, and here we have 5, what their standard inputs are. So for shell and the pick command, their standard inputs are the terminal, as you would expect, so you can type things in. And for the other 2 programs, Shell and Cisco earlier, those are also termed. But if you'll notice on the 3rd line, ID3, that shell's standard input is F0. That is actually the flash drive, and it's specifically the startup file that was used to bring up the FU menu that you saw with the pick. So this gives you an idea of how standard input and standard output work on the OS9 command line. In summary, OS9 shares a number of concepts with Unix, but it's its own operating system with its own philosophy. The module is a core concept in OS9 and contains everything from executable code to data. IOMan is the module that is responsible for orchestrating the input and output. It delegates I/O for specific classes of devices to file managers. File managers in turn delegate the interfacing of specific hardware to device drivers, and device descriptors tie file managers and device drivers together. Finally, the path is IOMan's abstraction to access files and devices in a unified manner.